Hello, makers, and welcome to another episode of CADurday, where we share pictures of cats and use computer-aided design tools to make something awesome. In the makerspace, I'm working on developing some environmental sensors that will track things like temperature, humidity, barometric pressure, and air quality using common, off-the-shelf electronics. Of course, no electronics project is truly complete until a suitable enclosure has been built to contain said electronics and keep them protected during operation. While it is not uncommon to see repurposed Tupperware containers or plastic storage bins used as improvised project enclosures, having a custom designed enclosure adds a level of polish and professionalism to any DIY project. Before we get started, it's worth pointing out that project enclosures are an often discussed topic in the maker community, and as such, there are a ton of great resources already out there to help you get started or provide inspiration. One of my favorite maker websites, hackaday.com, has a large collection of articles covering many facets of enclosure design. In the search box, just type in the word enclosure and you'll see what I mean. There are many ways to fabricate an enclosure. Cardboard can be a quick proof of concept when first laying out a design. Laser cutting can create large or small enclosures from wood or acrylic. And 3D printing can create a wide array of enclosures with complex geometry or parts that snap together. Which technique you choose is largely a decision based on the needs of the project and your goals as the maker. The makerspace at Exploration Commons has 3D printing, laser cutting, and CNC routing as possible techniques for fabricating a project enclosure. For today's project, we'll be using 3D printing. Let's take a look at the parts that are involved in this project, all of which are available online and have been sourced from Amazon.com. First, we have a Sharp GP2Y series air quality monitor that can detect smoke and dust. The sensor operates by shining an infrared light into a detection chamber and sensing the reflected light as dust or smoke particles pass through. To force air through the case, we have a single 20 by 40 millimeter fan, and it will operate at low speed to allow time for the dust particles to be detected by the sensor. To read the sensor and communicate data back to our server, we have an ESP8266 Wi-Fi enabled microcontroller and a small breadboard to make electrical connections. Finally, to power everything, we'll dig into the junk box and rescue an iPhone charger to provide 5 volts USB. Since these parts are part of a larger project we'll be featuring later, I'm not going to cover the programming or electrical work necessary to get them working together. Today, it's all about designing the enclosure. The first step is a survey of potential design constraints. The manufacturer's datasheet for the dust sensor has specific instructions for how the sensor should be mounted inside of the application. To prevent contamination of the sensor and avoid measurement errors associated with stray external light, the sensor will need to be mounted with the circuit board side facing away from the outside of the case and electrical connectors facing down. Another consideration will be how the device is mounted in its final position for operation. Will it sit on a table? Be mounted to the wall? Drawing some information from makers who have crafted mounting brackets for Amazon Echo Dots, I think we'll design an enclosure that attaches to or integrates with the AC adapter. This way the sensor can hang just below the wall outlet, be out of the way of anyone working in the room, and have a clear path for air to enter and exit the enclosure. When designing an enclosure for a project, I like to have CAD models for all of the parts that will go into the enclosure so I can easily visualize what the final project will look like. What is important here is to have models that accurately show the location of mounting holes, electrical connections, and be dimensionally accurate. It's not important to have pretty, well-polished models that can stand on their own. A few rectangles, squares, or cylinders are often all that is necessary. Before spending the time and effort creating these models, check online resources like grabcad.com or Thingiverse to see if other makers have posted models of the parts you're using. All the parts that I'm using today were found on grabcad.com, so I downloaded the .step file for each and imported them into Fusion 360. The dust sensor was missing the circuit board, so taking a few moments with a caliper, it was easy to add that feature to the model. Let's get started. The first thing I'm going to do is set the scene by importing a standard AC wall outlet and defining the wall surface. This is not technically necessary, but I think it's quite useful in helping us visualize the design as it evolves and takes shape. Let's add some color to the wall and outlet to make this look more natural. The first part we'll import is the power adapter and get it placed in the wall outlet. Now let's place the sensor and the fan. Remember, the sensor must be positioned horizontally and with the electrical connections facing down. The fan will pull air through the sensor, so at some point we'll need to design a bracket that will join the two together, but also secure to the case. We'll cross that bridge shortly. With the fan and sensor positioned roughly, let's bring in the electronics board and see where a good place for it might be. Some things to keep in mind. We'll have to power the electronics and have enough room to route cables and make connections. Since the wires for the sensor are facing down and only a single wire needs to be run from the power adapter, I think we'll place the electronics underneath of the fan and sensor. One of the greatest challenges in designing any part is always keeping in mind the assembly process. In CAD, it's very easy to move and position parts in a way that is not possible in the real world, or would create a headache when it comes time to assemble a finished project. How will wires be routed? What order do the parts fit in? Is there enough clearance? Now consider the limitations of 3D printing. One side of the project will have to be facing the build platform, and as such should be flat and free of features. While it is possible to add supports to that side if necessary, I like to avoid it altogether and plan for one side to be the build platform side. The first idea was a simple box with two open faces, allowing easy access to the internal components, and a cover that would seal the enclosure. Aesthetically, this is about as exciting as homework over the weekend, and is perhaps a little too simple. Thinking back to how the project will be assembled, I think we first need to join the sensor and fan together with a bracket such that they can be treated as one component. It will be secured to the case by bolting through the fan to the case and then to the bracket. Ultimately, I want the case to have only one open side, and for the parts to slide in and then be bolted through. The sensor has four 2mm mounting holes that came with some hardware already. Since this is a low-stress part, undersizing the holes on the bracket will allow the M2 machine screws to bite into the plastic, forming a strong enough bond. The idea is to have four bolts that will enter from the side of the enclosure, pass through the fan, and then fasten to the plastic bracket, sandwiching the fan between the enclosure and sensor bracket. One of my favorite 3D printing tricks when it comes to fastening hardware is to embed hex nuts in the printed part such that they become encased in the finished print. When slicing the part, just prior to printing, add a color change command to force the print to stop at the last layer before plastic is printed over the hex nut. This fake color change causes the printer to pause and sound an audible alarm letting me know it's time to insert the hardware. While it is possible to undersize the holes for the four larger bolts as we did for the sensor, having machined hardware allows for easier assembly and greater durability. Now that the sensor and fan can be treated as one unit, and we know how it will secure to the enclosure, it's time to reimagine the overall shape of the enclosure, taking into consideration our previous requirements. I've chosen the build platform side to be the side that faces the wall, and the open side to be opposite of that face. To create the shape of the enclosure, I'll draw a line around the profile of the sensor and fan, leaving room underneath for the electronics. The wall thickness for the enclosure will be 3 mm, so offsetting the drawn line by 3 mm and then extruding will give us the shape we want. Next, we'll need intake and exhaust ports. I'll use the projection command to project the geometry of the fan onto the enclosure wall and then perform an extrude cut to create not only the exhaust port, but also the holes for the bolts. Just how easy this was really highlights the usefulness of having CAD models for the parts you're working with. I'll repeat the same process for the air intake by projecting the intake hole on the sensor to the corresponding enclosure face and extrude cutting. Next, let's position the case under the power adapter and imagine how it might be secured to the case. I measured the CAD model as well as the power adapter, and they're only off by a millimeter at most. I'll use the measured dimensions in creating the geometry that the adapter will slide into. I want the fit to be snug, but not impossible. At this point, I exported the enclosure and printed just the power adapter bracket. This way I can test the fit as designed and come back and make small adjustments as needed. From within Prusa Slicer, it's possible to make plane cuts of an object to break it into multiple objects. I use this technique to print features of an unfinished design that I want to test fit in real life without having to print the entire part. Overall, I'm happy with how the power adapter fits, so now it's time to move on to the final feature of the design, the lid. Immediately it becomes apparent that the lid will be press fit into the case and held by friction. To create the lid, I'll project the enclosure geometry onto a new sketch and use the offset command to create the sidewall. How much of a gap to leave between the enclosure geometry and the lid sidewall will require some trial and error. To start, I'm using 0.1 millimeters of clearance and the sidewall will be 1 millimeter thick. In practice, I found that 0.1 millimeter works well when the lid is printed in draft quality. It fits snugly and is secure. However, when printing the part at a higher quality setting, the lid no longer fits properly or is snug, and as a matter of fact is quite loose. Once again, be mindful of print settings, as it is very common to print in draft quality when designing something to save time, but when set to fine quality, some parts may not fit as intended. With the lid complete, the last detail needed is the routing of the power cable. Digging through the random box of cords, I found the thinnest cable and measured the diameter with a caliper. Using that measurement, I created a sketch on top of the enclosure at the front and used the extrude cut to create an opening to pass the cable through. The last step was to project the new opening onto the lid so the sidewall will have a corresponding gap, allowing the cable to fit neatly into the enclosure. Finally, I'll round a few edges and corners to smooth out some sharp edges, and the project enclosure is complete. The final assembly went smoothly. Sandwiching the fan and sensor bracket together and sliding the assembly in until aligned with the four holes was easy enough. I used a screwdriver to hold everything in alignment and one by one secured the assembly using 4 bolts. The bolts I had were just a little too long, so a few plastic washers were used to adjust the fit. Earlier in the design phase, I should have considered the hardware length of what I had on hand. For now, I'm going to tuck the wires in, and when the electrical design phase is done, I'll come back and trim everything down. Overall, there is ample room in the enclosure for the microcontroller, and I hope to add additional sensors such as temperature and humidity later on. Routing the USB power wire went exactly as expected, and the lid fits wonderfully. All of the tools, software, and machines used to develop this project are available for use in the makerspace at Exploration Commons. It is my hope that this project has given you inspiration to learn more about computer-aided design as well as insight into the possibilities and joy of making. If you have any questions about CAD, the makerspace, or Exploration Commons in general, please don't hesitate to reach out to us. Thank you for watching and good luck.